something strange shows up when you look at how galaxies move. You'd expect them to drift apart as the universe expands. And for the most part, they do. But there's a pattern buried in the data that doesn't quite match that idea. Our galaxy isn't just drifting with the flow. It's moving in a specific direction. And it's not alone. Thousands of nearby galaxies, entire clusters, are all heading that same way. Not because of expansion, something else. Something with mass. It's not where you'd expect, and it's not something we can see clearly, but whatever's out there, it's affecting everything around us, and we're caught in it, too. If the universe is expanding, then galaxies should all be moving away from one another in a smooth pattern. That's what Edwin Hubble showed nearly a century ago, and it's the basis for how we understand cosmic expansion today. But here's the twist. When astronomers began measuring galaxies in more detail, they realized something didn't quite fit. The numbers didn't line up the way the neat math of expansion said they should. Some galaxies weren't just drifting away with the expansion of the universe. They had an extra motion on top of it. Almost like they were being pulled in a direction that couldn't be explained by expansion alone. Think about it this way. If you're standing by a river, you expect the water to flow smoothly downstream. But imagine if in the middle of that river, you notice patches of water swirling off to the side, caught in hidden currents. That's exactly what astronomers were seeing when they looked at the local universe. The Milky Way wasn't just going along for the ride. It was moving with a kind of urgency, a velocity pointing toward a very specific region of the sky. This discovery came from painstaking measurements of galaxies and clusters in the 1970s and 80s, pioneered by leading scientists such as Brent Tully and Alan Dressler. By mapping their redshifts, basically how their light stretched as they moved away, astronomers could calculate how fast they were receding. But then they compared this with the galaxy's actual distances measured using methods like Cepheid variable stars. The mismatch was obvious. The expansion didn't fully account for the speed. The galaxies had what's called a peculiar velocity. Motion not caused by the universe's expansion, but by gravity tugging on them. That's when the mystery deepened. These peculiar velocities weren't random. They seemed to point in roughly the same direction, as though a hidden hand were pulling entire clusters of galaxies towards some unseen mass. And when astronomers traced it back, the motion was heading right into a region of the sky behind the dense plane of the Milky Way. A place that's notoriously hard to observe because it's clogged with stars, dust, and gas. So, what could be hiding there? Astronomers gave it a name before they even knew what it really was. The Great Attractor. A massive concentration of something that had to be bending the flow of galaxies across hundreds of millions of light years. And the strangest part, we're caught in that flow, too. So, what exactly is this thing that's pulling us? You'd think with a name like Great Attractor, it would be something obvious, like a massive black hole or a bright galaxy cluster glowing in X-rays. But that's the thing. It's not obvious. It's not even clearly visible. When astronomers first noticed this strange motion, they hoped they'd eventually point a telescope at the source and find some enormous object, something they could photograph, catalog, and move on. That didn't happen. What they found instead was frustrating. The part of the sky where the pull is coming from is buried behind the thickest part of the Milky Way's disk. We're talking billions of stars, thick clouds of dust, gas, and all the things that make our galaxy beautiful, but also completely opaque, invisible light. That region is so blocked off, astronomers gave it a name, the zone of avoidance. Not because there's nothing there, but because it's where telescopes just can't see. And yet, something behind that zone was tugging on galaxies across hundreds of millions of light years. So the next step was to look at it differently. Instead of optical light, astronomers switched to radio waves, infrared, and X-rays, types of light that can cut through the dust. Radio waves, for instance, sail unimpeded through interstellar gas to map neutral hydrogen in galaxies. Infrared reveals cooler dust and star-forming regions that optical light can't penetrate. And X-rays highlight the scorching hot intracluster medium of gas plasmas reaching millions of degrees. Bit by bit, they started to piece together what was hiding behind the curtain. And what they found wasn't a single object. The Great Attractor isn't like a planet or a star or even a black hole. It's more like a gravitational hotspot, a region where the density of matter is higher than average. It's made up of hundreds of galaxy clusters and superclusters, all tangled together in a part of the cosmic web that's unusually packed. One of the major components of it is the Norma cluster, a huge collection of galaxies located about 220 million light-years away. That's just one piece of the puzzle. There's also the Norma wall, a long filament of galaxies that stretches even further. And beyond that, structures like the Centaurus cluster, the Hydra Centaurus supercluster, and several others are all mashed into that same region. Now, you might be thinking, if we can't see most of it, how do we know it's there? Good question. We know it's there because of how galaxies move. It's like trying to find the shape of a rock under a bedsheet. You can't see it directly, but the way the sheet bulges and folds tells you where the mass is. In this case, the sheet is the universe and the bulges are the strange movements of galaxies. When you see everything in one region flowing toward the same point, something massive has to be there. But even with all this, there's a catch. The Great Attractor isn't really a single thing in the way we'd like it to be. It's more of a gravitational focal point. Not a destination we're falling into, but a region where gravity happens to be strongest in our part of the universe. And it might not even be the biggest player. Later discoveries like the Shapley supercluster, located even farther beyond the Greater Attractor, could be pulling even harder. In other words, the Greater Attractor might just be a pit stop in an even bigger gravitational flow. Something we didn't know about when the name was first given. So when we say our galaxy is being dragged across space, it's not just heading toward one enormous object. It's being pulled by an entire landscape of invisible structures, clusters, walls, filaments, and probably a huge amount of dark matter we can't detect directly. The Great Attractor is just the part of that landscape that we happen to stumble on first. And the scary part, we still don't know exactly how big it is or even where it ends. You've probably heard that the universe is expanding, right? That galaxies are all moving away from each other because space itself is stretching. That's true, but it's only part of the story. Because while the universe does expand on large scales, gravity is still doing its thing on smaller scales, pulling matter together wherever it can. And in the case of the Great Attractor, that pull is strong enough to override the expansion, at least in our part of the universe. Here's how it works. Picture a balloon with dots drawn on it. As you blow it up, all the dots move away from each other. That's cosmic expansion. But now imagine that a few of those dots are connected by strings. As the balloon stretches, those particular dots don't drift apart as much. The strings representing gravity are holding them together, fighting against the expansion. Now, scale that idea up. The Milky Way isn't just sitting alone on the balloon. It's part of a network of galaxies, groups, and clusters that are all tugging on each other. And in our case, there's a very clear direction we're being pulled toward that massive region we call the Great Attractor. It's not some clean linear motion, either. It's a tug-of war. Expansion is pushing galaxies apart. But the gravitational well created by the dense region around the Great Attractor is pulling us inward. This is what astronomers refer to as peculiar velocity. Motion that doesn't come from the overall expansion of space, but from local gravitational effects. In our case, the local group, which includes the Milky Way and Andromeda, is moving at about 600 kilometers per second in a specific direction relative to the cosmic microwave background. And we're not alone. Many nearby clusters are moving in roughly the same direction, like leaves caught in a slow but steady current. But here's where it gets even more interesting. That pull we're feeling, it's not constant. It's shaped by everything around us. Galaxy clusters, dark matter, filaments, voids, they all influence the way we move. Some parts of the universe have more matter, so they pull harder. Other parts are emptier and in a strange way that can push galaxies away. This isn't just motion towards something. It's motion through a gravitational landscape full of hills, valleys, and hidden forces we're only beginning to understand. And this is where dark energy enters the picture. While gravity pulls things together, dark energy is pushing everything apart. It's not just expansion, it's accelerated expansion. That means over time, the universe is stretching faster and faster, making it harder for gravity to keep things bound. The balance is delicate. Right now, in our local region, gravity still wins. That's why we're falling toward the Great Attractor. But over the next billions of years, dark energy may win on larger scales. Galaxies not already gravitationally bound to each other will drift so far apart that they'll fall out of each other's reach entirely. So even though it feels like we're being pulled towards something huge, the truth is more complicated. We're not spiraling into a single object like water down a drain. We're moving along a path carved out by mass and gravity while the universe itself keeps expanding underneath us. It's like walking down an escalator that's slowly stretching in every direction. And here's the part that really changes how you think about it. The Great Attractor isn't dragging us in like a vacuum cleaner. We'll probably never reach it. In fact, we might already be past the part of its influence that matters. What we're really seeing is the after effect of that pull. The result of living in a region of space where the gravitational tide has been flowing in one direction for a very long time. So yes, we're moving. Yes, something massive is guiding that motion. But in a universe that's expanding faster and faster, we're also being stretched away from everything else. It's not a chase. It's not a destination. It's motion inside a system that never stops changing. Up to this point, it's easy to picture the Great Attractor as the main thing pulling the strings, the big gravitational boss in our region of space. But here's the twist. It's not alone, and it might not even be the biggest influence on our motion. The more astronomers zoomed out, the more they realized the Great Attractor isn't the final answer. It's just one part of a much bigger picture. Let's talk about that bigger picture. In 2014, scientists redefined the structure of our local cosmic neighborhood. They mapped out not just where galaxies are, but how they're moving. And what they found was that all these motions, including ours, seem to flow along connected pathways like streams feeding into a giant river. That river is what they now call the Ionia supercluster. Ionia is massive. It spans over 500 million light-years and contains more than 100,000 galaxies, including the Milky Way, the Great Attractor region, the Virgo cluster, and many more. Instead of thinking about galaxy clusters as isolated islands, Ionia shows that they're part of one enormous interconnected structure. We're not being pulled by just one object. We're being guided along gravitational slopes that span hundreds of millions of light-years. The Great Attractor is just a dense region sitting inside this supercluster, acting like a bend in the current, not the source of it. Now, here's where things get even weirder. In 2017, another idea came into focus. Not just attraction, but repulsion. Some researchers noticed that part of our motion might actually be the result of us being pushed away from a vast underdense region of space, a giant cosmic void. They called it the dipole repeller. At first, this sounds like nonsense. Gravity pulls. It doesn't push, right? But here's the catch. A region of space with much less matter than its surroundings creates a kind of gravitational imbalance. If you have a dense region on one side and a vast empty void on the other, the net effect is a push away from the void and a pull toward the denser zone. It's not that the void is actively pushing, it's that there's nothing there to hold us back. It's like being caught between a wall and a cliff. The wall doesn't move, but the drop behind you has nothing to stop you from falling forward. This repulsion contributes significantly to our local group's peculiar velocity, complementing the attraction from the Great Attractor and helping explain the full dipole pattern observed in the cosmic microwave background. The dipole repeller lies roughly opposite the direction of the Great Attractor. So the way to think about it is this. We're being pulled forward by overdense regions like the Great Attractor and Shapley supercluster, while also being released or unbalanced from behind by this massive void. It's a push-pull situation on a scale that's hard to imagine, underscoring how voids, often overlooked as empty space, are dynamic sculptors of the cosmic web, driving large-scale flows just as powerfully as galaxy clusters, and potentially influencing the universe's overall expansion dynamics on scales up to 1 billion light-year. And it doesn't stop there. There are other structures involved, other clusters, other walls of galaxies, other filaments feeding into this motion. Space isn't empty. It's full of these invisible highways, and galaxies tend to move along them like traffic on a one-way street. The Great Attractor got the name, but it's not the only one shaping the road. That's why our galaxy's motion isn't just about where we're going. It's about where we're coming from, too. We're caught in a gravitational tug-of-war between dense regions and cosmic voids. And the direction we're moving in today is the result of that long, complicated interaction. Not one cause, not one destination. A combination of invisible forces stretching across space, all steering us through a web we can barely see. For all the progress astronomers have made, the Great Attractor remains one of those mysteries that refuses to be tied up neatly. We know it's there, but we can see the motion it causes, but the details, the what and the how much, are still frustratingly out of reach. The first unknown is the true size and mass of the region. Some estimates suggest it's equivalent to tens of thousands of Milky Way's worth of material. Others argue the bulk of the motion we see isn't just from the Great Attractor at all, but from even larger structures farther away, like the Shapley supercluster. The problem is the farther out you look, the harder it is to separate one gravitational influence from another. It's like standing in a crowded stadium and trying to figure out which voice is pulling your attention when everyone is shouting at once. The second uncertainty is the role of dark matter. We can see galaxies, clusters, and hot gas, but they don't account for the full gravitational pull we measure. That means a significant chunk of the Great Attractor's influence may be coming from dark matter, the invisible scaffolding that makes up most of the universe's mass. We don't know how it's distributed in that region, how dense it is, or whether it forms a smooth concentration or something more chaotic. We're basically drawing outlines of a shape we can't directly see, and hoping our indirect measurements are accurate. Then there's the question of whether the Great Attractor is even a destination at all. The name suggests we're on a one-way trip toward it, but cosmology doesn't really work that way. Because the universe is expanding faster and faster thanks to dark energy, it's possible that we'll never reach it in any meaningful sense. The pull we feel today could simply be part of a larger flow, one that will eventually be overwhelmed by cosmic expansion. In other words, we might not be falling into the Great Attractor. We might just be sliding past it on the way to somewhere else. On top of that, the zone of avoidance continues to limit how much we can see. Even with radio and X-ray telescopes, we're still missing details. Surveys keep uncovering new galaxies hidden behind the Milky Way, and each discovery slightly changes the picture. The Great Attractor might turn out to be not a single dense region, but a complex layering of structures, each adding to the overall pull. And finally, there's the broader uncertainty. How do we even define the edge of something like this? With galaxies, you can point to a shape. With black holes, you can define an event horizon. But with the Great Attractor, it's more like a gradient. Where does it start? Where does it end? How do you separate its pull from the surrounding superclusters and voids? These aren't small questions. They cut right to the heart of how we map the universe and describe its structure. So what we have for now is a paradox. We know enough to be sure the Great Attractor exists, but not enough to describe it fully. It's there. It's powerful. It's pulling us. And yet, the closer we look, the more it seems to blur into the larger web of the cosmos. It's easy to hear about something like the Great Attractor and think, all right, cool. There's a heavy spot in space pulling stuff toward it. So what? But here's the thing. This isn't just about motion. It's about how the universe is wired together. Understanding why our galaxy is moving the way it is leads straight into deeper questions about structure, gravity, and what the universe is really made of. First off, this kind of motion exposes the invisible. We can't see dark matter. We can't see the shape of gravity itself, but we can see how galaxies respond to it, the direction they move, the speed they're going. These aren't just numbers, they're clues. When you see thousands of galaxies drifting toward the same region, it tells you that something massive is sitting there, even if that something isn't giving off light. That's how we learn where dark matter is concentrated, not by spotting it directly, but by watching how it bends the motion of everything around it. That's also why peculiar velocity, that extra motion on top of cosmic expansion, is such a big deal. It shows us where the gravitational landscape has bumps, slopes, and valleys. Cosmic expansion stretches the universe uniformly, but gravity creates deviations. By measuring those deviations, we're effectively creating a map of the universe's hidden mass. No telescope can show you that directly, but the motion of galaxies does. And then there's the larger idea, structure. The universe isn't just a random scatter of galaxies. It has shape, a web-like shape full of clusters, filaments, walls, and voids. It's not neat. It's not symmetrical. But it's not chaos either. These flows of galaxies, these giant streams heading toward overdense regions like the Great Attractor or Chapelli, reveal the patterns underneath. They show us that we're part of something structured. And that structure tells us how matter has evolved since the early universe. On top of that, this whole situation puts our galaxy in context. We tend to think of the Milky Way as a fixed point, a home base floating in space. But it's not fixed. It's part of a long chain of motion stretching far beyond what we can see. It's orbiting the center of the local group, which is moving toward the Virgo cluster, which is caught in the flow toward the greater attractor, which itself is drifting towards something else. It's motion layered on motion, and none of this happens in isolation. Every flow, every pull, every repulsion reshapes the large-scale structure of the cosmos. Even the way galaxies collide, merge, or scatter across space is influenced by these giant flows. Understanding the Great Attractor isn't just about one direction we're heading. It's about the bigger game of cosmic evolution. Then there's the weird philosophical side of it. We're not stationary. We're not drifting randomly either. We're being carried along in a current that we didn't choose and can't escape. And we're only just starting to realize how deep that current goes and how complex the forces are that shape our motion. It matters because it reminds us that the universe isn't static. It's not just sitting there. Everything is in motion, guided, shaped, and influenced by things we still don't fully understand. And if we want to figure out the true architecture of the cosmos, we can't ignore these flows. They're not noise. They're the signal.